All right, in this section, we're going to look at what kind of information we can get from the graph of a function. So if we have the following graph, you should be able to identify this as some kind of root function. All right, so we need to find what is f of -3. So when x is -3, what is the y value? The y value is 1, so this equals 1. When x is 0, what is the y value? The y value is 2. When f is -5, well, when x is -5, there is no graph. So -5 is not even in the domain of this function. So we say that does not exist. It's not possible. What about f of 5? Well, this arrow means that it will go on, right? So if we were to find f of 5 will be 3. Later on, when we learn about how to use transformations, you will be able to identify this graph as the graph of square root of x shifted to the left 4 units, but it will be a couple lectures away. What is the domain and range of this function? So the domain, remember the domain is all valid x values. So we saw that -5 was not a valid input. So the first valid input is for x equals -4 and all the way to infinity. So it will be -4 to infinity for the domain. And then the range is the resulting y values, or y values. So notice that when x equals -4, the y value is 0. When x equals -3, the y value increases to 1. So the y values start at 0, and then if this goes on and on and on, it goes on to infinity. So if we were to put this graph in a box, the box will be starting at 0, and then it will go all the way up to infinity. It includes 0 because f of -4 will be 0. I'm sorry. All right, and then where is the function increasing, decreasing, or constant? So I start with the first value in the domain for x, and I look from left to right. What is happening to the y values? So if I look from left to right, the y value is 0, and then the y value increases, and just keeps on increasing. So where is the function increasing? For what x values? Values are the y values increasing. So from -4 to infinity, for those x values, the function is increasing. So we write it like this, -4 to infinity. The function is not decreasing or being constant on any portion. It's increasing everywhere. The reason we don't put bracket is because at -4, the value is 0, is a constant. It's not something increasing or decreasing, it's constant. What is the local minimum, local maximum? This one actually doesn't have any. It has this minimum here, but since it's the only minimum, we would call it a global min. It has a global min. So it's minimum for everything. We'll talk more about local min and max shortly. All right, so if we look at the graph of a function, okay, the domain is going to be all the x's, all the valid x's, and the range is going to be all the outputs. So if you can box your function in between two vertical lines, that will give you the domain. And if you can box your function between two horizontal lines, that will give you your range. Okay, so what if I have a graph like this? maybe you'll recognize this as a power function graph. Power function graph with x, with p even and positive. What would be the domain for this? Well, the domain is all the x, so it's everything between negative infinity to 0, but doesn't include 0. I don't have function. At 0, there is no y value, but everything after 0 all the way to infinity, I have function. So the domain is everything between negative infinity and 0, union 0, infinity. What about the range? Well, I noticed that the y values range from, well, from something close to 0 all the way up to infinity, but they never reach 0 because this line does not cross the x-axis. If you recall, we have what we call a horizontal asymptote as at y equals 0. So the range is 0 to infinity with parentheses at 0 because it doesn't reach 0. Okay, and this is just the theory of increasing and decreasing and local min and max. So if I have a function depicted like this, I see that if I look from left to right, on the interval AB, on the x interval AB, the y values are increasing. So we say that the function is increasing. As soon as I hit B, from B to C, the function is decreasing, and from C to D, the function is increasing again. The local min and max. So finding min and max is important in many applications. For example, if a function represents revenue or profit, we are interested to find its maximum value and where does that happen. Or if a function is cost, we would want to minimize that, so we want to find a minimum value. So for example, if I have a function that is graphed like this, I have a local maximum happening in here. And why do I say it's a local maximum? Because there might be other maximums. So if I look locally, so if I look at A, for example, and this is f of A, if I look locally, so if I look at x values close to A, so what we call this is some open interval around A, okay? So it could be like A plus 0.001 and A minus 0.001. So if I look very close, the y values are less than this peak right here. So everything to the left of this is less than this. That's what it means to be a max. But this happens only locally. So I can't take my interval to be from here to here. Well, this actually, yeah, like if I continue this, there are other values that are greater than this. So if I only look closely, if I zoom in, if all the values are less than that, then we say that that's a local max. So this is a local max, this is a local max, and save for local min. So if I look locally in here, everything to the left of this is greater than it, and everything to the right of it is greater than that. All right.